So what we're talking about today is the photoelectric effect. And this is one of the phenomenon that bothered classical physics that could not be explained. We've talked about a few. The one that we first talked about was the cathode ray experiment. And now I wouldn't say it was a phenomenon. It was just something that was in labs that they just didn't know how to explain. Certainly quantum mechanics wasn't necessary to explain what's happening. But in the cathode ray experiment, basically J.J. Thomson was able to find a mass to charge ratio for the particles that were coming from the cathode, all right, that was about something in the order of 2,000 times lighter than any other particle they've done similar work with, or at least 2,000 lighter than, let's say, the lightest known atoms like hydrogen. So we found a piece of an atom, okay, and that, of course, was the electron. The other issue with, or a phenomenon that was not explained, or I would say was one of the first phenomenons that needed to be explained in terms of what the physics of the day could not, all right, was the ultraviolet catastrophe, or the spectrum of light, okay, from a black body radiator, okay? And of course, we've talked about this. Black body radiator was giving a spectrum that was not taking off into an ultraviolet type of scenario. Remember, we talked about this. If you think about this in terms of frequency, okay, the higher frequency, the earlier and lower energy heat, this would be intensity. So the temperature was lower, you would have some sort of spectrum like that, and as the temperature increased, it would come up, go up, and then, but the problem is, even highest temperatures, we'd have a peak temperature, but it would come down. Whereas the mathematics of the day said that the intensity would go up, and essentially the frequencies would reach those of X-rays and gamma rays very fast, when in fact experimentally it never did that. And that was the ultraviolet catastrophe, which essentially was solved by Max Planck, okay, or Planck. And of course, with his mathematics, he basically line fitted and found a way to show that he basically made something called Planck's Law, which included Planck's constant, which was a proportionality constant that was used to talk about the discriminant energy levels that the oscillators in a black body could have. So when you heat an object, thermal energy makes atoms, and atoms have charges, they have electrons and protons, and when they vibrate and move, they give off electromagnetic radiation. Okay, that was all known. But he's basically, his work was trying to show that this energy was somehow quantized. All right, so Max Planck was more about the idea that the emission of light may occur in discrete energy packets, okay, or quanta. Now, it was Einstein who took the work of this Planck's constant, more notably this idea of discriminant, discrete energy levels that these vibrating oscillators in a black body could only accept and only release. He kind of took, and definitely took, this work and was able to express it in terms of light is quantized. See, Max Planck was talking about basically the matter could only accept a certain energy level to, and he was talking about these oscillators, we now know to be atoms, of course, could only move at certain discrete frequencies, which is again based upon times the Planck. So this energy, certainly, of these oscillators moved in only certain discriminant energy levels based on the frequency and Planck's constant. So this Planck's constant is a lot like, I would always say, like ladder or rungs on a ladder. Okay, energy levels can go up, but only discriminately to different or succinct energy levels, nothing in between. And that's, again, I could talk about that another day. But what Einstein did, okay, Einstein, and again, a really important figure here, said that, okay, yeah, that's great, but now let's think of light as quantized. It's the reason why these oscillators move is because it's the energy that's discriminate in light, okay? And what he did, he used that idea to essentially explain the phenomenon of the photoelectric effect that could not be explained through classical physics. So essentially, through the work of Planck, he was able to use his work, and then with some interesting way to think about this, was able to explain that light is quantized. And interesting enough, in 1905, Einstein basically published three separate papers that he got published in a science journal. He wasn't working in academia because of, well, so it says that he really made a lot of people mad when he was going to school, as he challenged most of his professors, and couldn't get recommendations, so he was working in a patent office. But in the 3 years, he published three papers. One was for the photoelectric effect, the other one was for Brownian, explaining Brownian motion, which essentially discovered the atom, okay, mathematically, and three, the theory of special relativity, which of course turned Newton's laws of motions kind of upside down in terms of how we can think about um, these phenomenon. In any case, my focus is the photoelectric effect, and this is the one that he got the Nobel Prize for. All right, so let's start. And again, I went through that so you can see how this certainly. And again, when we talk about energy of a photon, it's equal to Planck's constant times the frequency. And often you will see people write the photon underneath here, and it's a good practice to do that because I want you to understand that we're talking about light traveling in a packet of sort, light acting like a particle. And this was a monumentous, okay, explanation of this phenomenon that, again, could not be explained by classical physics because, all right, of issues I'll explain. But think of this. It turned the world on its head because for the first time, we're treating something that we definitely know to be act as a wave. Light acts as a wave. We saw today in class the Young experiment where we took light and we shot it through two slits, open slits, and we got a diffracting pattern where we had what? We had places where there was constructive interference and destructive interference. And then we got this diffracting pattern. And I shot a laser through that, and we saw that. So light is definitely a wave. But here's what Einstein said. To explain the photoelectric effect, and using the mathematics first built upon by Max Planck to help with the ultraviolet catastrophe, we can say that light also has particle behavior, as if it had mass. And this is the first place that we have mass or particle and wave duality. And that's a cornerstone of quantum mechanics where we're headed. Quantum mechanics means energy is quantized. Discrete energy levels go in and out of matter, and that mass could have wave and particle behavior. So let's get started about what the phenomenon was and what classical physics tried to explain, or where it fell apart. So what was the photoelectric effect? Well, the photoelectric effect was a scenario or a phenomenon that we knew in nature where we had a metal object. So this could be any metal. All right. And what we did is we basically took a light source that shot out light. Okay. And so it shot out light. For instance, let's just say it was shooting out red light, and would hit the surface. And what would happen, okay, is electrons would be ejected. So the idea here is that the energy of the light would somehow eject the electrons with a certain kinetic energy, a certain motion. All right, so the photoelectric effect would say, well, if you shine different types of light with different frequencies, we know from our spectrum of Roy, G-BIV, and of course here would be the infrared region. This is the ultraviolet, and of course we should know at this point that this is longer wavelengths, and of course they get shorter as the frequency increases. And by the basis of our energy equation, energy is equal to Planck's constant per photon of light times the frequency. So energy, of course, is greater on this end than it is here. Okay. Now, so the idea here is we shine light at a metal and we could see electrons and measure their speed coming off. So the phenomenon was you just change the light and different electrons of different speeds come off. Now, what really happened was a scenario like this. We would shine light on a metal and we would expect the light to eject electrons. But some metals did not eject electrons when you first shine the light, or in this case, we'll make that light called red photons, an individual, okay? And there was no electrons. They didn't detect electrons. So classical physics, based upon Maxwell's equations, something I'm definitely not going to go over here, but Maxwell's equations, and he was someone who kind of helped unify the idea of Faraday's work of electricity, magnetism, motion, and how light works, basically using Maxwell's ideas of classical physics. Essentially, an electron can have any energy it has, okay? And of course, light is not moving in packets or photons, it's continuous, okay? So from his work, essentially the intensity of the light, okay, would be equal to the energy of the electron. Which means if I increased and make this brighter, okay, make this red brighter, okay, then I would eventually be giving this metal enough energy, assuming light is a continuous energy wave or source, and that electrons can exhibit any energy, and the metal can accept any energy. Of course, we're assuming a non-quantized world. And that did not happen. So if the light did not eject any electrons, classical physicists, they just said, make it brighter, and it will. So they made it brighter, okay? They made it brighter, which means they increased the intensity. So therefore, it was a darker red. Now, and what happened was it doesn't emit any electrons. You see, in order for the metal to emit electrons, we needed to reach its threshold minimum amount of energy. Einstein called this binding energy, meaning we somehow had to reach the minimum amount of energy to pull the electron away. The red light did not have enough energy to do so. Okay? And classical physics states you just make it brighter. You're going to give it more energy because light is a continuous form of energy. And if you make it brighter, you're going to put more energy here and you'll eventually reach the binding energy and remove it. But it didn't work. It didn't work. And so that was a major problem. So Einstein said, of course, the energy is going to travel in packets. So this making it brighter doesn't work because the individual packets of the light do not have enough energy individually to eject the electrons. And let me explain that. So here's a table, okay? And you're going to go to this table. We're kind of looking down at a convention, and we have people working here. This is the top of their heads. This guy's got blue hair, and we've got someone else sitting here and someone else sitting here, and they're working. and they're helping sell something at this convention, and it's shrunken heads, let's say. So we got shrunken heads that we're selling. And you badly want a shrunken head. Who doesn't? So we have people online to buy these shrunken heads. So these are my people with long necks are online waiting to buy these shrunken heads. It's not a bad line. Now, each person is carrying $9. Everybody in this line is carrying $9. So when they get to the table to offer their $9, okay, to the person who is selling the shrunken heads, they say, well, no, you do not have enough energy. But what about all my friends behind me? They've got enough energy, don't they? But if every individual person is bringing $9 and the cost, let's say the cost per shrunken head is $10, I don't care how long this line is of people who have $9 apiece, they cannot get the shrunken head. You need to have at least 10. So the red line, or the red photons that were emitted by this light source, okay, individually the packets of energy were like $9. And each one, let's make it 9 joules if you want to use energy terms, even though 9 is pretty high for a single electron. But the point is that each one of these packets traveling, when it hit the object, didn't have enough money or energy to pull an electron away, or what? Get the shrunken head. That's how it really worked. Only when, and only when, I erase this money value here, and I make this every particle have 10, can now each individual what? Photon would hit, and an electron would be emitted. Now, the key to the photoelectric effect is this, individual packets. So we can only eject the electron when the individual packet, which we call a photon, this is called by Einstein, he coined that photon, which is a packet of light, had enough energy by the what? E equals Planck's constant times the frequency. And we say photon right here. And of course, it's based upon the frequency. So red light with the metal that we're using, and let's just make this metal iron for all intents and purposes, okay? The individual packets of light were not what? High enough to eject the electron, okay? And only when you make the light not brighter, but change its frequency so each packet has more energy. So if this was a green light, okay, I guess I should write in green. If this was a green light that hit the surface, let's pretend that was enough energy. What do we know about green light? Well, red light has a certain wavelength. Green light has a shorter wavelength, therefore higher frequency, and has a higher energy. The packets of green light would be enough to yank electrons away. So only when you change the frequency of the light did the electrons go, and that was so against classical physics. Just to say, hey, take any old light, increase its intensity, make it brighter, and you're going to give electrons more energy. Okay, and of course that did not work. So Einstein, using Planck's quanta idea of light being quantized, and them traveling in these packets of bundles based on what? Photons, and this equation, okay, explain that. Now, interesting enough, if you give the individual photons more than they need, just like so let's say we gave them $12 to buy their shrunken heads, they would individually get their shrunken head, but then they would have $2 extra. Instead of getting $2 back as change, that $2 of extra money, extra energy, is used, and it's used to what? Make the electrons go at a certain kinetic energy. So we've got green photons. Let's do this down here. We have green light. It's hitting our metal surface of iron, and we've reached the threshold of a certain frequency so that each bundle of energy has enough energy, and electrons are emitted. And their kinetic energy, their motion, okay, energy is dependent upon the extra, in this case, the extra $2. So their speed that we would see, we can measure that velocity is based upon how much extra. So what Einstein postulated was that what we had here was the photon energy. So this right here is the energy of the photon that got accepted by the metal. You have to be at the threshold. If it's not high enough, if each bundle doesn't have a high enough frequency or energy, it won't work. So assuming we're beyond that, okay, we know that this threshold he called binding energy. This is the energy to release the atom. And the extra, read all about it, the extra energy was the kinetic energy that the atoms had. Okay, so to find the speed, okay, if we can measure the speed and we know the energy per photon, because it's easy to measure the frequency of the light, we can measure the binding energy. Now, the binding energy is the energy it takes to pull an electron away. And what's interesting is different elements have different binding energies. Yes, different atoms hold on to electrons differently, right? Iron, okay, is pretty reactive, but not as reactive, let's say, as sodium. So this would be sodium. Sodium loses electrons much easier. We should know this by now. So, therefore, if I shoot it with the same green light, okay, the photon's the same, but because it holds on to electrons so much weaker than iron, its binding energy is going to be a lot less, which means what, party people? The kinetic energy is going to be a lot more, okay? Energy of the photon, okay? Energy of the photon is, the photon here, Photon, is equal to the binding energy plus the kinetic energy of the electron. All right? Now, of course, back to classical physics, what they stated was, hey, okay, if you reach the threshold and you've got more electrons moving out, if we make this brighter, we would expect, based on our classical physics, that we would make these electrons move faster. And guess what, party people? That doesn't work. If we make this brighter, the electrons did not go faster. You know what they did? If you made it brighter, you just had, come on, say it. Yeah, good for you. More electrons being emitted at the same energy. Because if you're making it brighter, what are you really doing? Aren't you just sending more photons? Aren't I just sending more people to the table with the right amount, with the extra amount of energy? Right, so making it brighter, you're just making more packets. And if more packets of people come to the table, you're going to eject more what? Electrons, or in this case, shrunken heads. So making it brighter and understanding we're dealing with a photon, this packet idea of light, okay, making it brighter, all you're doing is, of course, adding more individual packets of light that have enough energy. You're going to eject more electrons, but you won't make them faster. You only make them faster if you do what? Increase the energy of the photon, which is dependent upon the frequency of the light. That is the photoelectric effect. And you may say, okay, great, cool, whatever, but the photoelectric effect and understanding it and harnessing it is the basis for solar panels. Hey, electrons are coming off from using light. Photons of light from the sun are hitting a solar panel and ejecting electrons, or making electrons move, or making charge move. Hey, a current can happen through that. If you don't like that, take out your iPhone or any smartphone you have. It's taking digital pictures. The idea that we're taking light, okay, in our atmosphere through a lens, and we're able to capture that into ones and zeros into a digital image, is due to some kind of photoelectric effect. To know what the picture is using a digital camera is using this idea of the photoelectric effect. So we're surrounded. Any light sensors, Okay, so considering how many people have smartphones in their pocket and the ease at which we take video, digital video, we have to give thanks to this phenomenon that's now been explained. Okay, so now I want to quickly take you through an animation to make sense of all of this. Okay, so here is a great animation. Helps us understand Einstein's work and his explanation of this photoelectric effect. And it's made by PHET. Great animations they have there. Okay, you should go to their site and certainly see many there. So in any case, what we're going to do is we're going to have a metal, and here's our metal, and we're going to pick sodium. So this is a metal that we know is pretty reactive, and we're going to basically shine some red photons on it. And you can see that in this animation there is no electrons being ejected. And of course we know why, because each photon, okay, being emitted by this light source is going to the table with not enough energy or not enough money, okay, to eject the electron. So classical physics would state, make it brighter. You're going to give it more energy. So if I make this brighter, 100% intensity, then I should start to see some electrons, because light is a continuous wave. Well, no, it's not, and it didn't work, and we couldn't explain it. So back down the intensity, the only way we can start ejecting electrons, according to Einstein, was that if each individual photon had higher energy, meaning a higher frequency. Energy is equal to Planck's constant times the frequency. So let's move. Look at our spectrum, red, and we're going to move toward the blue or the ultraviolet. So we're going to increase the frequency. Look at this, is the size, a nanometer is the size of the wave. So if I'm going to move this way, you can see that my wavelength is decreasing, and we should know that means that the frequency is increasing. So only when I hit the threshold, now threshold is the amount of energy that would eject the electron. So only when the photon reaches that minimum amount, there we go. So I'm pretty close to the threshold. Theoretically, if I match the threshold, electrons would be ejected but not go anywhere, okay? But they would definitely go where, because there's always going to be some, in space, some kind of potential difference to go. Now you say, my gosh, they're going pretty slow, okay? Going pretty slow. So classical physics states, well, all you have to do is make this brighter, and they'll go faster. So we're going to make it brighter, and what do we find? All we've done by making it brighter is having more electrons being what? Ejected. They're not going faster, because more people are going to the table with the what? The same extra money. And it's the extra energy from the photon that gives these electrons energy to move. Okay? So I don't care what you do with the intensity, let's lower the intensity down. Okay? You're going to see a lot less electrons. That means there's less what? There's less photons. All right? So this should make a lot of sense. I turn the intensity off. There's no electrons. Make it go brighter. I'm sending more photons, because I'm already at the what? I'm at the threshold energy. I'm going to emit some. If I send more photons and more people with the right money, with the extra money, okay, by making it brighter, all I'm doing is sending out and ejecting more of these shrunken heads. They're going at a speed that's related to the energy per photon, the extra energy. The only way that I can make these guys go faster, if I change the energy per individual behind the shrunken head. By what? Increasing my frequency, which is the same thing as decreasing the wavelength. So if I make the light become what? A higher frequency, now you can see that the energy, the electrons coming off, okay, are of a higher energy. Now you may notice something. At these light of a higher frequency, now you have faster electrons. And on average, you're going to have a lot more faster, because individual photons are giving extra energy. But you may be saying to yourself, well, Mr. Grodsky, why are some going faster than others? Well, think about electrons and how they are around in an atom. Aren't some electrons closer to the nucleus in a more stable orbits or regions we call orbitals? Yeah, electrons that we're extracting that are farther away from the atom, they don't have much energy left. That's why they're going slower. The electrons that require more binding energy. So you assume that all electrons have the same binding energy. You don't. We talked about valence electrons. These are electrons that are held on the outermost edge of the atoms. They're farther away. They're easier to remove. So therefore, they have a lot more extra energy than these faster ones. The ones held closer, okay, go slower. Why do they go slower? Because there wasn't a lot of extra money at the end because it took more energy to make them move. So it's really important you understand that. Okay, make this go to the ultraviolet region, and we're going to increase the speed even more. Okay, the energy per particle, and that was not explained. This is what they expected. They expected the result that I'm doing here by making the intensity go up, but no, it's about their frequency, and that essentially is what we talk about. Now, that was, again, that was sodium. Okay, let's go find that threshold again. That was around here. Okay, a little less than that. Let's try to find that exact threshold where electrons are just being barely emitted. And I may be around there. I might have to go greater because there's nothing happening. So just 140. Can I get a little bigger? Almost. Okay, so this is about the threshold. Okay, and that was sodium. What if I change this to copper? Notice the different color. Now, copper, we know, is a lot less resistive to losing electrons. That's why we make copper pipes. Copper doesn't oxidize. Hey, been through this before. Copper resists oxidation. We need a different oxidizer to do so. So copper has a different threshold. Make it less bright or brighter has no difference. The only way to eject electrons would be I have to make the what? Each individual photon have a higher frequency. And eventually we'd get there. So you look at copper. Copper resists losing electrons. That's because its binding energy is what? Much, much higher. It's higher threshold. So only when we get to the ultraviolet, maybe, if this works at all, there we go, somewhere in the ultraviolet region, am I ejecting electrons? Okay, and again, the ones going slower are the ones that have a higher binding energy that are close to the nucleus. Remember, all electrons are not in the same what? Energy levels. Electrons, as we're going to come to understand, are quantized as well. And that is the photoelectric effect. Okay, so your mathematics, okay, let's get rid of this. So the math that you're going to do is based upon this right here. We have the energy of the photon, and that's got to be high enough to overcome the what? The energy it takes to pull the electron away. So this is the binding energy, or the energy it takes to ionize. We can also call it binding energy, ionization energy, the energy it takes to pull electron away. And then, of course, what is the extra represents the kinetic energy. Okay, so all you need to do to solve these problems is understand that this energy of the photon, of course, is energy per photon, Planck's constant given to you in reference table, times the frequency of the light. Okay, and you can get that total energy. Subtract out, and by the way, the energy is going to be in joules. Okay, and then of course you subtract out the binding energy, okay, and you can get the kinetic energy. All right, these are all in joules as well. Or if you have the kinetic energy and the binding energy, you can add them together, and what's it going to give you? The energy of the photon. So it's really simple math, okay? And again, you're using your very simple energy equations, E equals h v, or frequency. We know the speed of light is equal to the wavelength in meters times the frequency. And we also know, if you want to put this together, it's very helpful, as you probably saw, frequency, when you solve for frequency, frequency is equal to what? Well, frequency is equal to speed of light over lambda. So when you write this, if this is equal to speed of light over lambda, you can put this in for frequency, and you get E is equal to hc over lambda. And those are all your equations. Of course, we know our kinetic energy formula, 1/2 mass mu squared. Hope mu liked the presentation. So go on to the math now. Use your key. Use the key to review the questions. Not difficult.